So, guys, what we're going to do today to start off is I'm going to review with you a good deal, because if you recall, what we ended on last class was doing a calculation for an acidic, no, sorry, not an acidic, doing a calculation for a basic salt. Let me just refresh your memory. We were looking at situations where we were dissolving a salt in water. What do I mean by a salt? Any ionic compound, okay? When you dissolve an ionic compound in water, sometimes the pH can drop below 7 and be in the acidic range. Sometimes it'll stay right at 7, and sometimes it can rise and become a basic pH. And what you will be able to do by the end of today, without doing any math, is to simply look at a salt, any salt I give you, and just by looking at it, be able to tell me this salt will result in an acidic, neutral, or basic solution. Okay? So that's the first thing that you'll be able to do. And the second thing you'll be able to do is do some calculations with it. And we did an example calculation right at the end of last class. We did it with the salt, sodium azide. Okay? So I'm going to review with you today quite a bit, just to make sure that this is solidified in your brain, because in all honesty, I think these concepts, these salt concepts, can be very challenging. Okay? You may disagree. I find them to be challenging, so I want to make sure that it is crystal clear in your brain. Okay? So, let's start off with an example. Let's say that we are dealing with this salt right here, ammonium chloride. The very first thing I do when I'm presented with a salt, you don't have to do this, I just find it helpful, is I always draw a line separating the cation from the anion. Okay? The next thing I'm going to do is list out my major species. Get in the habit of doing this, because this becomes especially important in chapter 15. Okay? 3 major species. And let's review the thought process here. Okay? Let's start with the cation. Okay? Cations in a salt can always possibly form some kind of base. Cations form bases. What base do you know that looks kind of like that? NH3, ammonia. Okay? Is ammonia a strong base or a weak base? Okay, weak. So I'm going to put a W for weak over this side of the salt. Let's look at the anion. Anions form potential acids. Anion acid, AA. What acid could possibly be formed here? HCl, strong or weak? Strong. Okay. Now, just to review with you, when we started talking about salts last class, we saw examples of salts that were strong. Do you remember what the pH would be if you had that combination? pH of 7. And the reason was because both things could form strong things, neither ion was going to react. And let me refresh your memory on why that was. What does it mean to be a strong acid or a strong base? Yes, sir?
It fully dissociates.
Okay, correct. Complete dissociation. Does that mean that strong things like to be together or apart? Apart. So strong things will not form. If you have an S over one side of your salt, that ion will not react. And it won't, because what would it form? HCl. HCl does not want to form, so that's not going to happen. Okay? So, as strange as it sounds to say this, the weak side of the salt, if you ever have a W above one side of your salt, that is the side that will, in fact, react. So let's think about what our reaction is going to be. Cations form bases. Question?
So how are you able to decide that like H4 is weak?
Because if I say cations form bases, what base do we know that looks like this? NH3, ammonia. And I know ammonia is a weak base. Okay? And since we just said that, okay, this is going to form a base. What base is it going to form? Ammonia. What's left? What's my other product? Okay, H plus, or you could write it as H3O plus, same thing. Okay? That's the reaction that we're going to go through. Okay? And to be honest, guys, this, I think, is the hardest part. Is just figuring out what is going to be, what's the reaction, what are my products. Remember, just like the example problem we did last class, we're going to put an ice table underneath this. And when we get to the bottom, we're going to have something that looks like this. Blah, 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 minus x. Okay? Let's review this too. Yes? Question? Yes, it is. This isn't NH3. NH3 is a weak base. Remember, think about what I've said this whole time. Cations form bases. I didn't say cations are bases, because this isn't a base. This is, in fact, a conjugate acid. The cations turn into a base. They are not themselves bases. Exactly. Exactly. Okay. Let's review, because we did this last class. Notice that I have not put a subscript letter there. Okay? And I told you that you can no longer rely on what kind of a K value is given to you in the problem. Are you given a Ka? Are you given a Kb? Some problems you're given exactly what you need, but some problems you're not. You're given the exact opposite of what you need. You've got to be able to understand and figure out yourself which kind do you need. And remember what I told you. Every reaction we have written in this entire chapter so far has been something plus water. Do you agree? Okay. The kind of K value that we use is dependent upon what is that something doing. And look, what is this guy doing? Is he giving away a hydrogen or accepting a hydrogen? Giving away. So that's by definition an acid. Okay? So, in order to solve this problem, I would need a Ka value, which might be given to you, but it might not. What if you were given this? The Kb value for ammonia. Okay? Remember this equation, which you don't have to memorize, it's on your equation sheet. And what is Kw again? What number is this? 1 times 10 to the negative 14th. Okay? You can, if you're given the Kb for a base, you can always solve for the Ka of its conjugate acid. Okay? So, let's get to an example problem. Okay? I'm going to help you start it, and then you're going to finish it. It says, calculate the pH of a 0.25 molar solution of blah, 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 blah. Okay? And then you're given a whole bunch of other information. That's the technical name for that, by the way. Okay? Now, guys, I chose this one for a reason. This is a salt. Can any of you tell me, like, immediately, where does the cation end and the anion begin? Okay, I'm hearing multiple answers. Some people are saying between the N and the H. Some are saying between the H and the Cl.
C and H. Oh.
Okay. Now, if you are concerned, how are you supposed to know? Here's how you're going to know. Okay? If you are being asked to calculate something about a salt, one of the sides, and only one, by the way, only one of the sides must be strong. Okay? Remember how we put letters W and S? Let's just back up for a second. If you have a salt that's strong, what's the pH?
Neutral.
Right. There's nothing to calculate. We'll talk about in a second what do you do if it's weak, but you won't be asked to calculate anything. If they're asking you to do a mathematical calculation, one side of your salt must be something strong. And I would hope that we have our strong things memorized by now. I know I do. Okay? You should be able to very quickly recognize things that become strong bases or things that turn into strong acids. Let me make sure you understand why the line is not between N and H. Okay? Pay attention to my words here. The anion becomes an acid. The anion is not itself already an acid. That's why the H is not included in the anion. Okay? What acid could this anion become? Perchloric. And that is one of our strong acids. This side is weak. This side is strong. Would I expect you to look at this and say, oh yeah, that's pyridine. Yeah, that's coming from the pyridine base. No, I wouldn't expect you to know that. But I would expect you to recognize the other side. Okay? If you see something that doesn't look familiar to you, it's weak. Because, again, I'm expecting you to be able to immediately recognize your strong things. So which side of the salt am I going to write my reaction with?
C5.
You got it. C5H5NH with a +1 charge. How did I know that? Because what is the charge of perchlorate? Because I know my polyatomic ions. And I know that this has a -1 charge, so this must have a +1 charge. You take it from here. Write out your reaction. Cation plus water. Predict your products. Set up your ice table. Do science. Guys, he asked a really, really good question because this is something that makes these problems difficult. Okay? I think most of you can probably figure out which side of the salt will be added to water. But here's the part that makes this difficult. When you're dealing with something that you're not familiar with, how do you know what that product is going to be? I mean, we keep saying the cation will form a base, but here's the thought process. Grant, you want to take it?
Because that one is a plus. So
Okay. You're right. Because this has a +1 charge, it is very likely going to donate that hydrogen, but here's how you know for sure, even more than that. If we're going to be forming a base, what is this going to act as?
Acid.
An acid. If the base is here, its conjugate acid is here. What do acids do? Acids give away a hydrogen. Okay? Here is another clue right there. Okay? You know the question I'm going to ask you.
Yes, it does.
Okay, but let's just make sure that we know how to answer that question, because salts are not as straightforward as a question where you're just straight given a base or an acid. You're given a salt. So how do you know how to answer that question? Does it make sense? Look at the product that's being made here. We're causing a reaction to occur where this is being made. If you've got this floating around in abundance, your pH will be in the acidic range. Is it? Yes. So we are in good shape. All right? So, from now on, when you're doing any kind of an ice table problem, any kind of problem involving an ice table, and you need to use an equilibrium constant, do not just blindly take whatever K value is given to you. Look back at your original reactant and ask yourself the question, what is this thing doing? Is it donating a hydrogen or accepting one? And then decide what kind of K value you should use. Okay? Let's just summarize this, what we've done so far. Cation, anion. If we had a strong, what was the pH?
7.
Okay. If we had strong, weak, which we did last class, it's basic. This is an example of what we just did a problem with. Weak, strong, acidic. And what we're going to look at right now, without any calculations whatsoever, is what happens here. The pH is not 7. Nope. It depends. Okay? Not enough information. Okay? That's exactly right. If you're given a salt and it's a weak, you cannot just look at it and say acidic, neutral, or basic. You must have more information. So what kind of information must you have? Well, let me tell you. Let's say I had an example like this. Copper fluoride. Do you agree it is an ionic compound? Okay. Let's go through the thought process. Cations form potential bases. What base would this be forming? Copper hydroxide. Strong or weak? Weak. I thought all hydroxide salts were strong.
Are you kidding?
No. That's just craziness. Which hydroxides are strong?
Group 1, Bacchus Senior.
Group 1,
Bacchus Senior.
Bacchus Senior. I've never heard that.
You had it.
D-A-C-A-S.
I mean, I got it, but I'd say Cabasser, but cool. Bacchus Senior. All right, fine. Okay. What acid could this side form? Strong or weak? Weak. Okay? You can't just look at this and say acidic, neutral, or basic. You must have additional information. What additional information? Here's what you must be given. The Kb for whatever the base will be, and the Ka for whatever the acid will be. And from there, it's very logical. If the Ka is bigger, it's acidic. If the Kb is bigger, it's basic. If they're equal, it's neutral. So, you have a textbook in front of you. Please go to page 628. You'll notice that there's a chart on that page with Ka values. You'll need to go to a second page. Go to page 647 as well.
I flipped to the right page.
Okay. Guys, on 647 is the Kb chart that you will need. You're going to need to be able to look at both of these. Watch the magic. Are you ready? Take the pages in the middle and fold them over. What?
Oh my gosh. I've actually never done that.
My God, that's why I make the big bucks. So, ladies and gentlemen, what I'm asking you to do on this slide, no math, it's just to look at the salts. Tell me, are they acidic, neutral, or basic? When is the only time you'll need to use these charts?
When they're weak.
If it's a weak.
Gotcha.
Now, some of these, it's a little bit tricky to figure out where the cation ends and where the anion begins. Because we're just learning this, I'm going to draw that dividing line on a few of these to help you out. Like that one. Some of these are a little harder than others. Okay, I think you can handle the rest.
So again, we'll be able to tell like this on the second column. Except for the last one.
Okay, so like let's say you were given this one, okay? If you're given a salt where nothing looks familiar to you, then it's a weak. Because remember, the strong things should jump out.
No, it's saying, look at those and
Like that jumps out at me because that's a metal, okay? has a trick to it.
What?
We were just talking about that.
I'm right.
At first glance, you would probably say strong, strong. Because NaOH, strong base, sulfuric acid, strong acid, right? Okay. You're right on this side. You're wrong on this side. Because,
What?
listen, do you remember
H2O.
last class? Hold on. Hold.
Oh.
We talked about polyprotic acids, acids that have more than one H to give. And we said that those polyprotic acids don't give away all of their hydrogens at once. One gets pulled off at a time, while one gets added one at a time as well. The acid that could form here is not H2SO4, it's HSO4 minus, which is a weak acid. So ladies and gentlemen, this is a basic salt. Tricky.
Wait, so how do you get like how?
In all of these anions, all of them, when you thought about what acid could be formed, you just tacked on one H.
True.
H, 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 H. You have to do the same thing there too. Just one H.
There's two NAs.
Okay, so ladies and gentlemen, let me wrap this up because we're about to move on to the last little bit in this chapter. Listen, you will be asked to do two types of questions with salts. In multiple choice, you're going to have situations like this, okay? You will be expected to look at a salt without doing any math or calculations and decide when that salt dissolves, are you going to have an acidic, neutral, or basic solution? Okay, this is big time in multiple choice. When you get to free response, you'll be asked to do calculations, but be aware, the only types of salts that you do calculations for are either strong weak or weak strong. Strong strong, pH of 7. Weak weak, you need more information. You won't be asked to calculate anything. If any of you go on to college and become chem majors, you may do calculations with a weak weak. We're not getting into it. Okay? Yep.
So there are some problems on the problem set that we use the tables for,
Correct.
but there won't be anything on the test that will use the tables.
If you do, I have to give you the value. I would give you the values right in the problem. Okay? Okay, ladies and gentlemen, for the billionth time, can you please tell me what it means for something to be strong? Complete dissociation. Well, guys, think about this for a second. If you say that, let's use an example like hydrochloric acid, completely dissociates, does that seem like something to you where the H and the Cl would be very tightly bonded together or loosely bonded together? Loosely. If they separate readily, that means they must not be held together very tightly, and that's exactly correct. Okay? Strong acids are strong. Listen. Strong acids and strong bases are strong because their bond strength is weak. Okay?
Wait, can you actually?
Let me say that again. Okay? Strong acids and strong bases are strong because the bond holding them together is relatively weak, easily pulled apart. Their bond strength is low. Their bond energies are low. Bond energy, remember, just means the energy required to break it. Okay? Weak acids, weak bases are weak, stay together because they have stronger bond strength. Okay?
If it's a strong acid, the conjugated base is weak.
Correct.
So that would have a high bond.
Correct. Okay? Another something you can think about is polarity. Now, we haven't talked about bond polarity in a while. I'm not talking about an entire molecule, just a single bond between two elements. Okay? There's a pair of electrons between them. What does a polar bond mean? Not a molecule, just one bond. What does that mean? Okay, there's a difference in electronegativity. What does the word electronegativity mean? Okay, attract electrons to themselves. Bonds that are very, very polar, meaning one of the elements is really hogging the electrons towards itself, like HCl. Okay, Cl is more electronegative. It's hogging those electrons. That leaves this bond very polar. That means this H can be very easily pulled off. And that makes sense. If it can be easily pulled off, it will be strong. Strong acid. Okay.
Are these older acid or
Bases too. Yep. All right. What does this word mean? Don't overthink it. An acid with oxygen. Okay, great. There's an example here, and I'm gonna write their formulas out so that you can see this. I'm gonna rewrite this one. Oh man. Okay. I want you to look at these 4 formulas I've written in yellow. Is any one of those one of our 6 strong acids? Okay. So I'm going to put strong. What about the remaining 3? They're all weak, okay? Out of curiosity, I want to see if you remember how to name acids. This is perchloric. What's the name of this? Chloric acid. Because it came from chlorate. If you ate something gross, it makes you feel ick or sick. What's the name of this guy? Chloris. This is probably the most challenging one. You're close. Hypochlorous. Because it comes from hypochlorite. All right, now, if you look at those formulas, they all have H. If I say that this acid is strong, this acid is weak, weaker, weakest. Can you give me a clue as to why we're seeing this trend? Increasing number of oxygens. Okay, that's exactly right. Ladies and gentlemen, the more oxygens there are in an oxyacid, the stronger it will be. Now, first things first, I want you to be aware that the hydrogen of these acids that will be donated is joined to not the chlorine, but is actually joined to an oxygen. Okay? If I say to you that oxygen is a very electronegative element, what does that mean to you? Okay? It's pulling all the electrons towards itself. That's what those arrows are showing. Well, guys, if all the electrons are being pulled to the left-hand side of this molecule, that's leaving this little bond right there very, very weak in strength. If that little bond right there is very, very weak, is it easy to pull off that hydrogen or very difficult? Easy. If the H comes off easily, it's a strong acid. Oxygens, 3 of them, again, pulling all the electrons this way. Is that making that bond weak? Well, kind of. Not as weak as that one. Okay? So we're increasingly holding on tighter and tighter and tighter to that hydrogen because there are fewer oxygens. Yes, Grant?
Is there a huge jump between recorded or
Yes. Like, huge.
why is it such a huge?
One oxygen apparently makes a huge difference in terms of sucking electrons to one side. It just does. Okay? All right. So we talked about that. Now, guys, this is the last slide. Okay? There are going to be certain places, probably in free response, where you're going to be asked to write equations. So here's the thing. Guys, you will have places where you are asked to write equations. You will be given those reactants in words, and you will not be given the products. And you need to know some of these acid-base reactions. If you ever see a situation where a non-metal oxide, don't overthink that, it's exactly what it sounds like. A compound with a non-metal and oxygen, SO2, NO2, NO, CO, carbon dioxide, any non-metal and oxygen added to water creates an oxyacid. Always. What do you call reactions? What's the type of reaction where you have one product? Synthesis. Okay? Don't overthink this, ladies and gentlemen. It's not as hard as it looks. Whatever your nonmetal oxide, whatever the subscript is for the oxygen, on the other side, it's going to be one more. So, let me give you an example. Let's say you were given a question that said, nitrogen dioxide gas is bubbled through water. Period. Write the equation. Okay? Acids always have H. What polyatomic ion is H going to be joined to? Correct. Nitrate, NO3, which has a what charge? -1. Hydrogen is +1. Now, it's not balanced. You'd have to go and balance it, but what we're focusing on here is, can you predict the product? What if I did this? Correct. H2CO3. What's the name of that acid? Carbonic. Ladies and gentlemen, anytime you drink a soda, carbon dioxide gas bubbled into water, you're drinking an acid. Sodas are acidic. Aside from the sugar, that's why they corrode your teeth. Erode, excuse me. Let me try this on you. What do you call a synthesis flipped around? Okay.
H2O.
All right, H2O. How about just PO3? They're not ions. They're neutral compounds. Okay? Now again, it may not be balanced, but you would do that later. Okay? Guys, a question like this, a decomposition, like these would say this gas is bubbled into water. These would say something like a sample of phosphoric acid is heated over a Bunsen burner. Period. Okay? Right. But they're not going to say that. They're just going to say write the equation. And they're expecting you to know that it's a decomposition and that it's this type of decomposition. Yes.
Do they expect you to be able to balance?
Yeah. I'm not taking the time to do it, but yes. That is a hard one to balance.
So balance it on the test.
Yeah. It'll say write the balanced equation. Okay. That's how acids are formed. This is how bases are formed. It's not that different. Instead of a non-metal oxide, now it's a metallic oxide added to water, and you get the base. Let's do an example. How about, How about that?
Where's the alcohol?
It's not balanced.
Oh,
But the formula for the hydroxide is Li plus and OH minus. Okay. How about that? Okay. How about wait, careful. What's the easy product here?
H2O.
Okay. Think about charges. MgO. Plus 2 minus 2. Now, it may not be balanced. Oh, actually, it is balanced. But, anyway. I'm not worrying about the balancing part. Okay. So, that's it. Yeah. Good job, everybody.